Hey, in my last video, I talked about how to read a psych chart. Now I'm going to go over how I actually use a psych chart in a real world application. Here, I'm looking at a basic air conditioning process, a central air handler in cooling mode, and there are some things that I know, and then I'm going to use the psych chart to attain the things that I don't know. And really what I want here is, what is the load on this cooling coil to accomplish this process? So let's go over the things that we know. First, outdoor air. I know how much outdoor air I need to bring in based on my ventilation calculations. So let's say that's 1,000 CFM. I also know the outdoor air conditions based on my design day, 95 dry bulb, 80 wet bulb. I also know the return air coming back to the system is 3,000 CFM in this case, and the return air conditions are approximately what my indoor set point is. So 75 degrees, 55% relative humidity, and then I know what I want out of this unit. I need 4,000 CFM of 55 degree air to condition my space. And so these numbers I attain from my space sensible load calculations. But what I don't know is the mixed air state after return mixes with my outdoor air, and then how much load is on my coil to accomplish 55 degrees. So I'm going to use the psych chart to plot this and determine those numbers. This interactive psych chart makes it super easy, saves me a lot of number crunching. But the first thing I'm going to do is I'm going to plot state 1 and state 2, outside air, return air. So state 1, as I said, was 95 degrees and 80 degrees wet bulb, which puts me right about here. And to make it easy, I'm just going to punch this in and get exactly what I'm looking for. I'm also going to set the flow rate so that I can do that air mixing calculation automatically here. So 1,000 CFM of outdoor air. State 2, my return air, is going to be about 55% relative humidity, which is right around here, and then 75 degrees dry bulb. But again, I can also punch that in. And the flow rate coming back was 3,000 CFM. Now, with those points plotted and with the airflows provided, this chart determines the mixed air state for me. So I can see below here, I'm at 80 degrees dry bulb, 70 degrees wet bulb. Now, the last piece is to get 4,000 CFM of air from 80 dry bulb, 70 wet bulb down to 55 dry bulb. What does this cooling coil have to do? I'm sizing this coil. Let's plot the leaving air state and figure that out. Now you can see from the psych chart, to get to 55 degrees in cooling, I am going to hit my dew point and it will saturate, which means I'll be extracting moisture. And so once I hit my 100% relative humidity line here, then I'll be following the curve all the way down to 55 degrees, or I can also just punch this in as 55 and 55. Now, to calculate my coil load, I'm going to take the enthalpies at my mixed air state and my leaving air state and use those to determine the load on my coil. So now that this leaving air state is plotted, this purple line right here, that represents the coil load. To calculate that manually, I could look at the enthalpies for both of the states of air here. So my mixed air state has an enthalpy of about 34 BTUs per pound of dry air. The leaving state is 23 BTUs per pound of dry air. I can use the total load equation using my mass flow rate to determine the load, or I can let the psych chart here do it for me. That's already a feature of this interactive psych chart. And at the bottom, you can see the load going from your mixed air state to your leaving air state. So this right here is the total load on that coil. This is the sensible portion, and this is the latent portion. So I'm looking at about 182,000 BTUs per hour. Another thing we can visualize on the psych chart is the transformation from 55 degree air entering the space to what our return air state is. If you were to draw a line from the leaving air state back to state 2, which would be at a very slight upward increase, that would represent the sensible and latent gains within the space. I'll put a link to this chart in the comments.